I think we will get started, and I'll introduce the first speaker, which is Sara Beery. She's an assistant professor in ECS. She's a ECS Faculty of AI and Decision Making and CSAIL. I'm not going to have enough time to do the intros, right? This is, I think, maybe on the website as well. But I just want to highlight a couple of things. She was a visiting researcher at Google working on auto arborist, which is just, I think, a really cool name. She got her PhD in computing and mathematical sciences at Caltech, received a number of awards, PIMCO Data Science Fellowship, Amazon AI4 Science Fellowship, also founding director of the Caltech Summer School on Computer Vision Methods for Ecology, and she works closely with the likes of Microsoft AI for Earth, Google Research, and Wildlife Insights. So please help me welcome Sara.
Hello, everyone. Let me just get my computer set up. Oh. While that's loading. Cool. So this panel is sort of broad, writ large, right? I think it's titled Sustainable Computing, or Computing for Sustainability for Sustainable Computing, this kind of like cool circular title. And I think that there are a lot of different faculty at MIT who work sort of in different areas that somehow touch on either sustainability, possibly climate change, and computing. And I know that the Schwarzman College of Computing is really intended, and one of the reasons I was actually really excited to join MIT was because of this intention to bring together computing, and my side, AI and computer vision techniques, and then these other areas of science to actually really start trying to tackle these very large societal problems that we're facing. So my work actually focuses primarily on not necessarily sustainable computing directly, but actually thinking about how we build methods, how we build systems, how we build tools to help us better monitor the environment at a global scale. And today I'm going to be specifically speaking about biodiversity monitoring. So how do we understand what living things exist on Earth and how that sort of very complicated system is changing and adapting with climate change? And how do we use computing to make all of that possible? So my lab's big goal, and one of our really big goals, is trying to think about this, monitoring biodiversity and detecting change in biodiversity, but scaling that up so that we're actually getting this across scales from macro level, like elephants, all the way down to microbes, globally, so really sort of around the world and in close to real time. Currently, we are really far from this goal. We understand very little about biodiversity globally, and what we do understand is usually very isolated to particular parts of the world. Now, why is monitoring biodiversity important? So we know that climate is changing. This is just looking at increasing global temperature. We know that there are things about the Earth that are fundamentally shifting. And what we've actually seen is that somewhat correlated with this, there is going on a massive extinction of species at a global scale. So these are just these nice sort of frightening hockey sticks looking at extinction rates expanding across the taxonomic tree. Everything from mammals down to reptiles and other vertebrates. And actually, though it's not shown on this plot, the estimates for insect biodiversity are possibly sort of even steeper. And it's not just that we're sort of in this mass extinction of species. And just to give this some context, the rates of species extinction now are actually higher than the last extinction of the dinosaurs. So we are currently in basically something like an extinction of the dinosaurs, this mass extinction event. And experts are terming it the 6th mass extinction that's happened sort of on Earth. It's not just that we're losing species, we're actually just losing living wildlife. So from just 1970, the WWF estimates in their Living Planet report that we've actually lost almost 70% of all living wildlife on Earth. That's just in the lifetimes of some people in this room. So this is clearly something that is both changing very rapidly And unfortunately, it's something that we really don't understand as well as we need to be able to mitigate it. And I'm not the only person, of course, who's interested in trying to understand why this is happening, where, and how we should allocate resources. There are thousands of researchers globally who are thinking about different ways to try to monitor this process. And particularly with recent advancements in hardware, this has really led to an explosion of data that is somehow used to monitor biodiversity. Everything from satellite imagery to these stationary networks. This is like, maybe 100 or 1,000 sensors placed around an area, giving you longitudinal monitoring. And increasingly, actually, something called community science. So I don't know if any of you have ever used iNaturalist. Have you heard of iNaturalist? Raise your hands. Yeah. If you haven't heard of iNaturalist, it is the best thing, I think. It's basically a way for you to go out into the world around you, take pictures of plants and animals that you see, that then get identified by the community and then turned into scientific species occurrence records in the Global Biodiversity Information Facility. And importantly, in the last 5 years, this has now become 90% of all of the information we have on biodiversity at a worldwide scale. Over close to 200 million observations collected by volunteers, which is really exciting. So we're seeing these huge explosions in the data that we collect. But one of the challenges is that it turns out all of the different ways that we're thinking about monitoring biodiversity, they're all proxy sensors. So there's no sensor we can put out that will just tell you what is the biodiversity of an area, how is that biodiversity changing. Instead, we collect images, we collect sound, we collect hyperspectral data from the air, we collect DNA, and then we process all of that data independently, and we try to turn that into information about what species exist where, how many. And so because there's no direct sensor, that means that as the amount of data has scaled up, our need for expertise to be able to process that data, to go from raw data streams to actionable insight, has really been outstripped. And so this historical sort of manual data processing paradigm really can't keep up. Just for context, for example, this is a picture from a network of camera traps, these static cameras that I placed in Kenya. We collected 10 million images last year. And me and an army of undergrads would not be able to label all of that data. Community scientists, aerial surveys, similar trends. And this really is why computer vision and machine learning has become such a fundamental aspect of the way that we monitor the environment, because we need to be able to automate the process of taking this data and turning it into something we can make a decision about or take action on. But there are a lot of challenges for machine learning in biodiversity data. This is just the first 16 million species observations at iNaturalist. These trends have continued since then. But what you can see is that the distribution of species on Earth is very long-tailed. This basically means that most of the things we see are just a very few set of common species. And then there's these orders of magnitude more species that are in this kind of like low data regime. They're rare, they're hard to capture, they're hard to see, they're elusive. Potentially they're endangered. And so if we estimate that we need around 100 examples of a given species to be able to robustly and accurately identify it with machine learning, okay, maybe there was like 10,000 species. This is now closer to 100,000 species we can identify. And then there's this entire tail of things that either we have seen maybe only once or twice, maybe we've never seen, but we know exists from the scientific record. All of that we really struggle to identify with machine learning because it's just not enough data to learn to recognize it accurately. And then on top of that, to make everything more complicated, biodiversity data can be very fine-grained. It's important from an ecological perspective to know the difference between an American crow and a common raven. But I'm sure many of you actually have no idea how to tell these two apart. It's actually pretty hard, and particularly if you don't see them together, it can be very difficult. Basically, the major things I see, it's a beak shape, and then the ravens are a little bigger. But relative scale is really hard for humans, actually. The thing is, this is just with images, but they sound very different. So this actually points to the need for multimodal monitoring, because it's very easy to tell these apart based on their call. It's very hard to tell them apart visually. And finally, and I think most insidiously, and this has been a huge amount of my research throughout my PhD and to today, biodiversity data is just not independently and identically distributed. The distributions of biodiversity are incredibly fluctuating, and they change over space, but they also change over time. And one of the biggest challenges here is that with climate change, they're changing faster than ever. So even if you had this perfect map, this perfect assumption, this perfect representation of data that covered the entire globe today, the distribution of species next year would be different. And then we don't have that map. What we have is, again, a biased sample on top of it. So this is where we have data in GBIF, in the Global Biodiversity Information Facility. You can see that there's pretty huge biases towards wealthy countries. This is where we estimate, this is an estimate of alpha diversity, the number of unique species that exist in a given place. And you can see here that these are almost anti-correlated. So we don't have information where we need it, and the information we do have rapidly becomes out of date. And it turns out that type of distribution shift is really a bugbear for the machine learning community. Our models do not generalize well out of distribution. And these types of distribution shifts are not unique to biodiversity. They're actually ubiquitous in real-world applications across the board. Everything from healthcare to understanding, poverty, changes over time, even looking at scaffolding for molecules. And it turns out that degradation in performance as you move out of distribution of the training data is also ubiquitous. So we see huge drops sometimes in performance, 16, 22%, when we actually try to deploy models out of the training data that they've been, out of the sort of distribution of the training data. And of course, remember, if the distribution of the training data is this year, it will be out of distribution next year. So there's no way to get around this. We can't get around the fact that the distribution will change. So we need methods that can handle this. And I think one of the things that's really a key factor here for ecology is that this distribution shift is actually innate. So every geospatial location has some distinctive habitat, so some visual distribution shift, and a distinctive class distribution. Like this is maybe like the relative frequency of the categories of interest will be different for every place on Earth. And actually this gets fractally different as you get to microhabitats because of the behaviors of individual animals. So if you're measuring something near the den of one species, you're gonna see that species a lot, even if it's actually generally rare across the board. And this is kind of true for wildlife. It's true for a lot of things. So this is just looking at the distribution of urban trees across North America. This was with that auto arborist project that you mentioned, which I also like the name. One of the things we found, if we look at the generalizability of machine learning models going from training on one city and testing on another, when you're trying to build models that can detect and categorize trees in urban forests, is that distribution similarity is a really key factor in performance. So we see these really similar structures in the distance between normalized per genus distributions, city by city, these pairwise, and then if you do this pairwise training and evaluation, you see this blockwise structure that represents similarity and difference, and kind of really points to how data value from a prediction standpoint sort of degrades as you move further away from where you actually want to use the model. Now, one hack that we found experimentally is you can just get robust models by making the problem easier, essentially. So if you need a model that will generalize well, aggregating up to really coarse levels of prediction, just saying animal detection, this we've found can generalize even out of distribution to habitats and to species that were never seen during training. And that's actually quite an important thing to explore. When do you have the generalizability that you need? Because this leads to impact. If you have a model that doesn't need to be customized and retrained with machine learning capacity and engineering cost for every single place on Earth, then it becomes widely usable and widely useful, and it ends up getting sort of integrated into the data processing pipelines of users globally with tons of different downstream applications. And this is kind of one of the reasons that something like a robust, reliable, generalizable model is useful even if it doesn't identify the species, because it's able to detect animals of interest and filter out sometimes huge amounts of data that didn't actually capture something of interest at all. And then we also look at active learning, right? How do we make that process of specializing that model less expensive and less computationally intractable for organizations. So really simple active learning processes, making use of a bunch of domain knowledge and like capturing the structure of the data that we capture. We can get the same accuracy with 99.5% fewer labels in some cases. And then there's also other ways to think about low engineering specialization, like trying to learn spatiotemporal priors that tell you where, based on a location and a time, what species are likely to occur. And this works really well. It tends to really boost performance, sometimes 10% performance accuracy improvement. But the danger is those priors are often learned on historic data. So as these ranges change, you're potentially degrading your ability to recognize species as they're shifting into new parts of the world, which is some of the most important information when we're trying to understand biodiversity change. So let me look. I've got probably 4 more minutes. I'll go through this pretty quick. So I'll just do a little bit of a deep dive into this one very specific project, which is looking at multi-view urban forest monitoring, and then some of the ways we're actually expanding that beyond just species ID. So urban forests provide huge benefits for society, and they're incredibly important for supporting regional biodiversity. They provide habitat, they provide sort of support for that ecosystem, but they also reduce air pollution, reduce energy use. Importantly, they're a key factor in reducing extreme heat islands, which have now, because of temperature increase, started to lead to human death in some parts of the world. But these are really not universally accessible benefits. There's pretty systematic data that shows that urban forests are much more likely to be large scale, have much more coverage in areas with high socioeconomic value. So this is just 2 different parts of LA. Pasadena, where I did my PhD, very green. Carson, much, much less green. And so while I was at Google doing my postdoc, one of the things we were looking at is predicting tree canopy. So just actually getting an estimate of what is the canopy cover. And this is now deployed in about 500 cities worldwide, and is actively being used by cities to do urban planning. But this is really high level. This is kind of like that animal detection problem. It's just tree detection. It's more generalizable because it's easier. But it turns out it's useful, right? So this is an organization we partner with called Tree Equity Score, and they're actually using that tree canopy cover to make an actionable score for a city across neighborhoods that lets them then think about where they need to allocate resources to try to reduce that inequity in access to green space. But it turns out that just canopy prediction is really insufficient for everything that a city needs to know about their urban forests, particularly as they're thinking about climate adaptation. So what we've been trying to do is move from tree canopy cover to individual tree detection and species categorization. And we're doing that through a combination of aerial data, usually high resolution EOS, and Google Street View, which was kind of the impetus behind this project, because we actually have a ground level view of trees in almost every city on Earth coming from Google Street View. But of course, look at the distribution. This is just across 23 cities in North America. It's about 9 million trees. The distribution you can see follows that standard long tail that we see in biodiversity all the time. A few species are very, very frequent. There's many that are sort of common, and then you have this long tail of rare species where there are very, very few examples. And we have multi-view data, so we both have aerial and ground level views for each tree. And one of the things that we've seen is that models trained on the full data set, sort of an aggregate, outperform any city-specific model. But it's not always true in practice that it outperforms for every city. So one thing I think is quite interesting here is then if you start to think about how this plays into resources, if you're the city of LA and you want the best possible model for the city of LA, actually you're best off training on the 400,000 training data, like training trees from LA, and then stopping there. Because the benefits you get from going to regional or global scale, scaling up to training on 9 million trees, are really little. And the cost of doing so from a climate perspective, just from a financial perspective, is quite high. And so I think we need much better understanding of data value for specific end users. How do we actually select the data that is maximally valuable to improve prediction for a specific user for a specific task? But we do find that combining information across data modalities achieves best results. Though interestingly, again, thinking about data value, street level data, though more expensive to collect, much sparser sort of in time and space, is much more valuable. You double the prediction accuracy going from aerial to just a single street level view. And finally, there is value, clearly, in this types of diverse large-scale data curation. You're not necessarily going to have an optimal model for every end user, but if you have a single organization that's investing in training one of these large-scale foundation models, it can have sort of an aggregate quite a lot of benefit across the board. So pushing for increased data sharing and kind of aggregating this data can provide value, even if it's not universally sort of equally valuable. The data is publicly released, which was a bit of a feat. It's the largest data set by an order of magnitude from Street View that's ever been released. And then most recently, we've been just going beyond the sort of image level, but actually trying to understand structure and over time. So here we actually use these street level views. We generate, using sort of modern segmentation and sort of generative AI, 3D envelopes. We then use biologically informed growth models to grow hypothetical trees into those envelopes. And these are actually rooted in environmental sort of initial conditions. And so as a result, what you can do is you can actually grow those trees backward and forward, and you can generate different possible environmental conditions and imagine sort of what that future growth of a urban forest in a city will be. And you can start exploring things like taking these leaves on and off, which lets you get a much better sense of that reduction in heat on like a really, really fine-grained scale based on different times of year. So there's a bunch of open challenges in this space. If anyone's interested, please reach out. Global and local distribution shift, long-tail distributions, sparse, low-quality, biased data, this need for interactive ecologist AI systems to get accuracy you need to make decisions, even if your model is imperfect. Building these systems that take advantage of all the different modalities of data we've collected, detecting and categorizing change, and improving limited interdisciplinary capacity. And we also have a Slack channel that's got maybe 2,000 researchers worldwide who are all working at this intersection of computer vision and ecology and conservation. Thanks.